Genome editing is, again, it's a molecular technique whereby we scientists can use any of a number of quite diverse technologies with really interesting names. Zinc finger, talons, and the one that most people have heard of, CRISPR, CRISPR-Cas9. These all refer to different techniques that have the same ultimate goal of not introducing foreign DNA like GMOs, but going into the genome as it stands. Sometimes you hear that it called gene editing. I think more technically we call it genome editing. Go into the DNA and make very small changes without introducing additional DNA from any other source. So it's kind of like a word processor searching a document for a misspelling and correcting that misspell, right? Do the search and replace. We end up at the end of the day with a genome that is still virtually identical to what it started, but with a fix, a correction to a very small segment. We're using CRISPR and other genome editing techniques now for a broad range of applications, both in agriculture to produce healthier, more nutritious, safer foods, and also in medicine. And it's not GMO. Under most legislative regulatory bodies do not regulate genome editing products because there's no foreign DNA introduced from other sources, and that seems to be the trigger. By bypassing that regulatory morass that GMOs in agriculture have had to face, the developers, both in public institutions and private industry, see a way to actually develop useful new products without having to spend millions and millions of dollars to satisfy regulatory requirements that may or may not be legit. So we're going to see more and more CRISPR products on the market in the future. We're going to see more and more genome editing in medical and health applications. So it's a bright field. There's a lot of stuff going on, a lot of developments almost on a daily basis to refine the techniques, to make it even more efficient, to apply it to a broader range of issues. We would like to correct things like muscular dystrophy, if we could, or things like the BRCA gene. If you're carrying BRCA and you have a high likelihood of coming down with breast or ovarian cancer, it would be very nice to have a simple, not particularly invasive technique to just eliminate that gene and that concern altogether. Now, the problem with that attitude is that nothing is 100%, right? Again, it goes back to the statistical likelihood that you can have a high degree of confidence that it worked, but you can't guarantee that it works. So it's still going to be there in the background. Some of the early experiments with therapeutic application of genome editing techniques haven't worked. They haven't worked. Some of them have been very promising, but some haven't. And so scientists now are looking at, okay, when the things didn't work, what went wrong? What can we do to improve that? And that's the basis of a lot of the technology right now. The research in the labs is to identify how can we make this more efficient, how can we make it more reliable, less invasive, to attack only this gene of interest, whether it's muscular dystrophy, BRCA, or any of hundreds of other genetically conditioned health and medical situations. How can we make it more reliable, safer, and so on? And almost every week I will see scientific articles saying, yes, we've been able to do this to overcome this problem. Prime editing is the latest one. Without getting into the technology there, it's an advance. It is an advance, and it's a very exciting field to be in. So for young people who are looking for a career, if you're interested in genetics, molecular genetics, this is the place to go.